everything. Welcome everybody to the final presentations of the wonderful work you did at the hackathon of the RIPE Atlas data. Thank you for participating, and thanks to Comcast for your generous sponsorship and for the idea to even do this. So we are really happy to have our first RIPE Atlas hackathon almost finished. And take it away. You will have a chance to present your work to the jury, and after that we will take a little bit of time to decide who were the 3 best ones. For the rest of you and also for the winners, we are really interested in the future cooperation. So this doesn't stop here. It doesn't end. We will love to stay in touch and to work with you further and with your friends. So tell your friends. The first one will be Valentino.
Well, yeah, hello.
Okay, because I have 2 hats, now I'm stopping being Mistress of Ceremony and Christian takes over.
Okay, welcome to the RIPE Atlas Hackathon 2015, the first one this year. Well, I welcome all the people in the audience and behind the screens, the millions. A special pleasure to welcome the jury on the left side, and maybe I think we're missing one jury.
Yes, she might.
Will be placed on the right side, so we're going to split the jury in playing good jury, bad jury in a way. But so without further ado, we're going to go with the first presentation, which is given by Valentino about Traceroute consistency check.
Hello everybody, I am Valentino from Roma Tre University, and thanks for accepting my application to participate to this hackathon. For this event I've been thinking to find out how consistent traceroute paths are over time. So my first idea, well, just a little bit of background. A traceroute path, we all know, can change over time due to many reasons, due to BGP changes, load balancing within provider networks, routing failures, link failures, and so on. So I thought it was interesting to find out how over time this information can change. My initial idea was this one. So if you have a traceroute path from the node 1 to the node 30, and it goes over time, so at time t is this line here. At time t plus 1 it goes towards 11 and 12 instead of 7, 8, and so on. And I wanted to encode this stability information through colors of nodes. So my input for the demo is this measurement. I selected a probe, and has been scheduled a few months back, and I'm streaming the results through the streaming API they just developed here at the NCC. And in this particular measurement, we injected some changes through selective BGP announcements because we wanted to check for a different project how well are one of our algorithms to find out network events work. So I knew already that there were many changes here. And this is the live demo. So here, colors, unfortunately, I did not manage to use them to encode the information I wanted. So they are randomly assigned. And within nodes, there's the last byte of the IP address. The probe is this yellow one, and the target is fixed there at the end of the. So what I like the picture, but at the same time, I think over time it can get really tangled, the graph. And even if it's just a single source destination pair, I think it's not really clear. I admit, but this is what I came up with in such a short time. So yeah, future work, make it work with the right colors, and of course extend to more than a single path, and maybe find a solution maybe in a different way, visualizing in a different way this kind of information, because maybe the force-directed layout I'm using it's not suitable for this kind of information. I don't know. And that's it.
Can you go back to the web page?
Sure.
So over what time span is this?
This has been streamed. So the whole measurement was one single day, so 24 hours, and the trace routes were performed every 15 minutes. But now it's getting new data faster, because the streaming API allows to play a stream of data in a faster way, let's say.
And in a 15-minute period, if it stops using one of the routes, will it go away and collapse down, or is this just sort of a historical summation
this is
of all
just an
routes?
historical. And the difference between the original idea and this implementation is also that one.
Okay.
So nodes that are not used shouldn't be drawn as connected in the original idea. But here everything is connected. Yes?
Two comments. First of all, I like it a lot. What I would be actually even more interested than the various traceroute hops is if the color coding or random circles or clouds around the traceroutes would show the AES.
Yes.
Because
actually it was, sorry.
I'm normally more interested if the AES path changes and it goes to different routers, or trombones of an ocean, or you see even some milliseconds in between, how it basically. Because when you have a change now, it could be a change in the same network, and it just takes a different path through the network, especially if you have a multi-link over multiple routers at the same time. What does it actually mean? It bypassed through another AS, and probably even the latency, which you don't see yet.
Yeah.
Was it always the same? Did it change 5 seconds, or was it tromboning over the ocean and suddenly it's 100 milliseconds more?
Yes, I agree totally.
But for the short time, I think it's quite cool.
Thank you.
Okay, I think, thank you, Valentino.
Thanks.
I guess has a lot of potentials. Our next presenters will be Barbera, Lara, and Luuk, and they will tell us about. I mean, we know the internet is not perfect, and they will tell us about a little bit about internet abnormalities. Okay, right now I didn't get in a chair.
Oh, that was yours?
No, it's fine.
Okay, no worries.
All right, so we are going to present this with the three of us. So that's Luuk, Lara, I'm Barbera, and we will have explored a bit about how can you sort of spot anomalies in the network. So we had a lot of ideas in front. So what we want to do is to sort of spot the less obvious anomalies. So for instance, small changes or repeating patterns. So we actually had a nice discussion with Emil about that. We also want to have a look at the difference between IPv4 and IPv6. Maybe even go fancy and apply some DNA analysis things to the data, and in the end we sort of did a data exploration with some basic statistical methods. So we used R for that, and then also maybe for some of you it might be interesting, we used it in R Studio, which is a graphical environment for that. So we used two data sets, the ping data to Facebook, and measurements to the University of Twente. So one of the things as feedback, so what we got from this file was that you got on one line one JSON entry, and I understood that's very useful because otherwise you get a very large amount of information at one time. In R actually, and especially with this R package, RJSON, that can't handle that. So you really first need to convert that to a big RJSON object before you move on. So the use cases where we see work for this is first of all to monitor a set of servers and then indicate whether something goes wrong. So you can have a look at variation in the response time and packet loss. And we also investigate difference between IPv4 and 6, and then looked at packet loss, really. So the first visualization, we thought, okay, graphs are nice, so let's make a graph. So here the nodes indicate, the darker nodes are the IP addresses of the Facebook servers, and the lighter ones are then the probes, which are pinging the server. Something went wrong actually here with the annotation, but those are details here. And maybe you can comment on this one.
Yeah. Well, we abandoned this particular attempt to visualize the data because the readability was really difficult here, and kind of maybe post-production of the visualization that was coming out of R was also complicated because the software that we were using later on was not recognizing these values as numbers, but as kind of graphical elements. That meant that you would have to retype each and every information, so that was really kind of complicating the process. So we abandoned this one and went for another attempt.
So first we removed everything. By the way, all the thickness of the lines is the variation in the response time. So what you can see actually is that something is happening here, but now you don't have labels. You do see that something happens here, but it doesn't tell you anything. So the next thing was then to just add at least location of the Facebook server so that you could get some information. Nevertheless, I mean, it looks pretty, but it's not really informative. So we tried another approach. It's just basically a box plot, sort of standard thing in statistics. And over here you see the IP addresses of the Facebook servers, and there the RTT, and sort of the width of this box plot then sort of gives you an indication about variation in the response time. So if that varies a lot, then something might be wrong with that particular server. We have also checked what the packet loss was, so if it is above or below a certain percentage, then you can sort of indicate it in red. And maybe you can comment on that again.
Yeah, so we were then experimenting with the ease of communication of kind of urgent attention in relationship to the RTT and whoever's operating and whoever's receiving the information. So we were looking into this option where the color is clearly using a conventional kind of color coordination, where red means alert, watch out, and this way of looking at it where maybe the focus was on the detail of the size of the typeface and use of color in the way that IPs are highlighted instead of the values on the chart. I would stop here and then I'll continue later.
So then,
okay, this would be me. Yeah, we also looked into differences between what we see on IPv4 versus IPv6. So this is the measurements towards the anchor at the University of Twente. On the x-axis, which is not visible here, is time. So this is a time span of around 1 month. And on the y-axis you see different probe IDs. So these are the sources that were pinging the anchor node at the University of Twente. Now whenever you see a dot within this plot, that means that there was a difference between v4 and v6. If both are not working, it's not shown in this plot. There are a lot of other tools that will show you if everything is broken, so we didn't want to focus on that thing. And if both are working correctly, you also do not see it on this plot. So every dot here means either v4 is broken or v6 is broken. The colors are used to depict whether that's V4 or V6. Now, unfortunately, the blue-grayish one means V6 is broken, and if you can see it, the black ones means V4 is broken. And again, so black means V4 is broken, but V6 is working, right? So you have an asymmetry, if you will, in that aspect. So the first thing you see, again, unfortunately, there's something wrong with IPv6 connectivity to the anchor. You see 22 nodes plotted here out of a set of 110. So 20% of the nodes has a problem connecting over IPv6. Now this is nice to see what has happened in the last month, right? But if you look at the top, you see one where there is almost nothing plotted, but towards the end there is one dot depicting that V6 went down. And that's interesting for operators. So we also filtered that stuff. And this applies some median stuff and see what's the normal status of this link. If I never have IPv6 connectivity, I'm not interested in the fact that, yeah, in the next 5 minutes it's also not working. No, I want to see if it has changed, right? So if you focus at the dots, you see that also, did this work? No. At the top one you saw, and you see, I hope you can see at least that there's also some changes here, and those are also visible in the filtered part. And this one, and we didn't have time to implement it, this one is also a candidate to hook up to the streaming API. So this can be used as a sort of real-time monitoring to see if anything is going on your network in a annoying way.
Okay.
You take over again?
Yeah. So the follow-up on this would really be, so now it's really snapshot, also for, so in his, what he presented, time is included, but in the other visualization it was just a block of 12 hours, and you actually want to have that in a certain time frame. So include time. R is not really interactive, so it would be nice to implement this actually in some way that can be interactive. And in the end, you do not only want to visualize it, but you also want to say something with statistics so that you can point to anomalies in the data set, and that is then reported to someone. So some remarks, R is nice for data exploration and analysis, but it's not so good for interactive stuff. And although you can change some things, it needs manual polishing if you really want to highlight the interesting bits. And then I'm
and very short summary of the visualizations. We found very interesting hacking and using scientific software for scientific research in visualization of network data, which is a hack in itself.
Okay, right now the protocol kicks in.
Yes.
That would be me. Yeah, thank you. I think we're going to have 3 minutes for questions. Right?
So you mentioned that the dots represent problems getting to the anchor, right?
Yeah.
How would you know if it's getting to the anchor or getting from the probe?
Okay, so to rephrase that, these measurements were from nodes towards an anchor. And this is different from the earlier plots that we showed, because those were measurements towards a set of servers, so to say. So you don't know where the problems are. No, I agree with that, yeah.
It would be nice to visualize that somehow, so you immediately know if the problem is closer to the source or closer to the destination.
Yeah, definitely. Yeah.
Or to be able to click on that one dot that was in the upper right and then explore.
Or just use shapes or something
Yeah.
to say this is a problem with the probe, and now there is suddenly a problem with the destination. So.
Yeah. We also want to do that with the number of hops in traceroutes and stuff like that. But yeah, time was rather limited.
Yeah, I like that you use the use case of comparing V4 and V6. This was one of the things that we wanted to see as an initial set of goals. So,
I also like the sort of bar block chart with the, it displayed several bits of information. It was also sort of the RTT on the vertical, and then the coloring by packet loss, which was a nice combination of two things in one sort of shape.
I guess that's also applicable to virtually any measurement that has RTT encoded into it, so DNS, HTTP pings, or anything, especially with Anycast, which we will hear about.
Yeah.
So that's good.
Okay, cool.
Yeah.
Thank you.
Thank you.
Thank you.
So the next presenter is Julian. Please come to the stage. And yeah, Julian is he was thinking about how to show how the Atlas network is global in a way. Because I mean, we know we have all over the globe. We have the probes distributed. A few more in Europe, some in the US. And whenever we're going to do a selection of probes worldwide, then it's usually a little bit biased towards the regions where we have more or less. And Julian thought about how to solve that.
Could you maybe say who are the 3 next ones so that they know?
Oh yeah,
because they don't know.
The next one will be Martin Levy. Then we have Katja and Michael, and after that we're going to have the disco team, whoever that is.
Could the judges just speak up just a little bit?
Sure.
Thank you so much.
Okay, so back in 2013, I was at a conference and showing RIPE Atlas there to people. And one of the slides we had there on a slideshow rotation throughout the conference was this one here, which showed a traceroute from, I think it was like 250 probes from all over the world to the conference location. And well, now if you tell people it's a global network and you only see a few dots in there, that's kind of missing the point. So that problem comes from the distribution of probes you see here. So you have like most of the probes in Europe and then lots in the US, but down here you can actually see one individual probe even though all the others are stacked together, and on the right you see the same. So it is global, but you don't really see it if you take a random sample from it. So to look at that in numbers, you see here the distribution of probes per country. I cut it off at the end, but you have the US with over 1,000, and then it declines very quickly towards where you have here like 10 to 1 or 2 probes per country. Now, I wanted to present the data on a map projection. So actually, what I needed to do is select probes based on whatever projection I'm using, which would typically be the Mercator one, which Google Maps uses. So on this one, I want to put a grid, and in that grid, I want to choose for each grid cell 1 probe and make the grid to that size, whatever I want the number of probes of. I could also use different projections because map projections are very political, because here you actually favor the northern and the southern countries in terms of area, and especially the northern, because down here you don't go as far down. There are also other map projections, like the Mulvite here, which is actually preserving the area of the countries, which is also supported by the tool I wrote. So that brings me to the tool. It's called S-Buckets for spatial bucketing, which then you can give it the number of probes you'd like, and it'll just give you the number of probe IDs that you requested. Roughly, it's not accurate, so it won't be 100 exactly that you get. It could be, but it doesn't have to be. And then these probes you can use in your measurement. So this is what it looks if you use the worldwide 500 random selection algorithm, which is already there in RIPE Atlas. And, well, you see it's missing Africa completely. That's the distribution that came out of it. And now with also 500 probes with that algorithm, this is what it turns out to be. And you can also select several countries. So if you like to only select Europe, you can give it a list of countries. And like, well, you can read the help in there. You can select several countries. So I did it with Germany and the Netherlands, and found some interesting things there. That's supposed to be in Germany, although the geolocation isn't. And that's also supposed to be in Germany, and the geolocation isn't. But if we zoom in closer, we see that we have probes all over the country. And of course there are places missing because, well, there are some places where just are no probes. Yeah, It's already all on GitHub. You can install it via pip, so it's just one command to install it. When you can run it, it uses the live data from RIPE Atlas for the probes. Or you can, if you want to do it faster, you can give it a data file which already has all of it in there. And you can change the protections. The default is for Mercado because most people will use that. And the max iter, the algorithm does like an iteration scheme where it changes the grid and selects then the probes, and it'll usually go to 100, so it doesn't take awfully long. Okay, that's it.
Thank you.
Can you scroll down a bit, just so I can get the title in the picture? Oh, sorry, the other way. Thank you. Yeah, the other down.
Okay, questions?
Well, I'm impressed that it is actually done. So it's already on GitHub, so that's a bonus. You can just grab it if you want to use it. My suggestion is that the better name for this would be Piketty, because it is describing the global inequality and actually fighting the global inequality. So that's my comment.
Doesn't have a Gall-Peters projection.
Okay, is it possible to plug in biases? So I want to say, give me 80% of the probes from Africa and the rest from Europe.
Well, you can say you'd like 300 from countries in Africa, and just give it a country list, and then append another one where you get 200 from Europe or something.
Yeah, I can always do that.
Yeah, but no, it's not in the code as that. Yeah, another feature in the code. So how do you get, actually that was a problem, how do you get that probe ID list into RIPE Atlas without using the API? It's just not possible. You have to go through the map and click on the probes individually and add them to it. So that would be very useful to just copy paste in it. If you do verbis, then you get actually the Kerr URL that automatically creates one measurement, but it just does a one-off measurement and doesn't do all the measurement things that you want. Then you can reuse that measurement ID in further API calls.
Right. So, and if I constrain it to a particular country, then it still applies the logic of it should be as widely spread as possible.
Yeah, it'll do it to the whole world, but the total number of probes that it yields will only be from that country. So it'll be a very fine grid worldwide, but it yields that number of probes.
And a question to the RIPE NCC from me: how hard is it to plug this into the Atlas selection process?
It looks promising.
But you're going to end up with isolated probes getting a shitload more measurements that they have to do.
Yeah,
We have mechanisms of dealing with that. So.
Well, one of the arguments against someone installing a probe in Antarctica is that everyone would want to use it. Just because.
We solve that by sending those people more probes.
Well, I don't think it's the problem of the probe being overloaded so much as the network that the probe is on.
Or satellite link.
But it will generate heat.
We'll be happy.
That's not good. But
Global warming.
Yeah.
Terrible thing.
Good job.
Thank you.
Thank you.
Thank you.
Okay, thank you. So, next one, Martin, it's your turn. I mean, what was interesting that the eastern parts of Germany had less probes.
Can the software install probes?
Yes, that would be cool. So to be honest, I can't really decipher the notes on the introduction to Martin. So I'm not really sure it's V4, V6.
So many of them. No.
Maybe it has something to do with the internet, right?
Yeah.
Okay, cool.
We're supposed to do internet stuff?
Yes, cool.
You're all Martins.
If you want, there's the last.
Yeah. It's an Anycast. You can talk to any one of them.
I
don't give me many jokes like that. Well, could you close your eyes so you don't know which one of us responds?
That would be Anycast, but I can also do multitasking. Martins, tell me.
Are we nearly there? Okay.
He said I was going to explain Anycast because I didn't know what it meant.
Yes.
I think
that's perfectly. It's also an educational exercise.
Well, that was not right.
Apple software is a bit hard to use. So.
Where's the prevent button?
Don't worry, your time doesn't start till you start.
Okay. All right. Can we start now?
Go.
There is laser, yes.
We have a logo.
Who else has a logo?
Who else has a logo?
How much time did you spend on the logo?
2 days, right?
We are sitting here. Okay.
No, we have a time limit.
I want my time back for that one. Okay. This is Team AnyAtlas. We all have either a vested interest in Anycast routing or no knowledge about Anycast routing, and so this was a positive all the way around here. So what we want to do is basically take data, use Atlas to actually measure some of the aspects of Anycast routing, and some of us have sort of played around with this before. But what we were more interested in is, could we get something different out of this data than we've tried to do before? So we've used this concept, the speed of light. It's a pretty big constant, but it tells you literally how long it takes to go from here to here. Except for in the internet, when you deal with fiber optic cable, things run a little slower. So what we've sort of tried to do is take the latency that's measured by a probe, convert that to what that distance would be, take the speed of light converted to fiber between where the geographic location of a probe is and where we think the destination is, and measure it. But not just measure it for any old destination, measure it for Anycast destinations. So the whole goal here is that we want to really show on an Anycast deployment, which we'll explain in a moment, whether we're going to the right location, or more importantly, could we actually come up with the next location to deploy in the world of Anycast. What's Anycast?
Hey. So I'm going to explain it because I had no idea what it means, so it's going to make me make more sense to other people. But if I say something wrong, you have to tell me. Anycast is, I'm some ordinary person, and I go to some IP address, and magically somehow it gets routed to a different place depending on where I am, and we're going to choose it so that it's fast for me, or at least that's the goal. Is this good? Yeah. Okay, so we're trying to figure out in our project whether connections are being routed most efficiently and how we could reconfigure the Anycast deployment to make it more efficient.
Yeah. So we have a slight failure in our presentation. I want to just move your head down. That's theory. Because in practice, life is slightly different, and hence that's why we want to do this measurement. So this is the method that we're using to measure. This is built into Atlas, and people have started well before Atlas was actually created to use this as a measure, as a way of measuring. So what we've got here is a simple script that you can run in many different environments, and it does a DNS query with a string from the chaos family versus the IP family. A DNS query we all know about, IP address for foo.com, and you get back an A record or a quad A record. In the chaos world, the only thing we don't care about addresses, we just care about a text string. So what we have is this sort of pseudo out-of-band capability to query something and get back a name. Here's an example from the Canadian top-level domain, .ca, where the different servers generate or respond with different names. And you can grab the script and go play around with it. But you'll notice we're getting things back like LHR or AMS, which means we're sort of getting stuff back that is tells us where the destination is, where we get connected to. Trouble is that the data isn't perfect. So even before we could process anything, we had to deal with certain important things. The randomness of the responses, and also people who just picked different names. So we found lots of things were airport names, except for MTL for Montreal, which is not actually an airport code.
Sorry, guys.
It is, but not in Canada.
But not in Canada. Yes, yes. So, and it's sort of important to say why we looked at Canada, because part of our team comes from Cira, which is the .ca domain guys. Bit of code to clean up stuff. Again, lots of pre-work before we could actually look at any useful data. What came out of this, by the way, was somebody needs to write a standard for this. So now we start looking at the data, and you're going to sort of see work in progress and hopefully for some end stuff. So, Tom, you want to explain what this is?
Okay. This plot, we have measurements that target the same Anycast target. This is a computer that's going to direct us to other computers, or an IP address that's going to go to different places. And we know, or we have a guess as to which destination was the closest one in kilometers and which one we actually got routed to. Each dot is a measurement. So this is the, oh shoot, I said it wrong. That's a different graph. We have the distance to the actual to the place we got routed and the time it took for the response. So we see as just as the server gets further away, it takes longer to respond. Yeah.
But it should never be below the line because that's the speed of light. You can't respond faster than the speed of light unless your geolocation data is wrong, which we've already seen on a previous slide, a previous presentation. So now let's sort of zoom in and we tried, these are various different methods of displaying the same data. Here you can see the probe number, which gave us the indication that we had.
This is the same graph as before, but zoomed in because there were a lot of outliers, and then keep going.
Well, the bottom line is the speed of light graph, and we can tell that we seem to have something below the speed of light here, or above it, sorry, if we think about it the right way. And then we also realized that we were seeing lots of different data because a single probe measured over plenty of time will give you a fast response occasionally and a slow response when the network's busy. The top line was what was it, Tom?
We just fit what we thought was the actual minimum time that it takes.
Right. So what we were trying to do here is to really work out whether we had clumps of data, clumps of probes going to the right place. And so we blurred up and made all the probes big so that we could sort of squint at this. And we just grabbed sort of work in progress here. We have to admit we never got to the final point with this. But what you see here is you see clumps of different colors.
Each color is a different city. So we see that this city, which is
Well, this was different data.
Okay. This city seems to be routing pretty well, and this one's taking longer because the server's further away.
Right. Tried a different way to try and... we kept looking at data, but we're going to get to the fun stuff in a second.
Yeah.
And then finally, we tried this, which was to completely remove the latency part and say, what is... As we know where a probe is in the world, we also can work out the distance to the closest Anycast server. So if that probe's sitting in Berlin, then Frankfurt is probably closer than Amsterdam, and Hong Kong is definitely a long way away. And although we see responses from Hong Kong or wherever, we know they're wrong, but we know what the theoretical distance. So we sort of measured theoretical distance, as in actual geography, versus distance calculated from latency. If it takes 100 milliseconds, well, it's this many 1,000 kilometers away. And guess what? You see a bunch of stuff pretty close to the line, which means that the theoretical and actual latency is pretty close to each other. Nothing to optimize. The trick here is to say everything above the line needs to be investigated in some way. Didn't get much further with that. Because we
did in a different way.
We did in a different way because we got this. When we finally realized, oh, look, let's look at temporal data. Let's look at this over time. This is what our ultimate goal was, to produce something cool, actually.
We also have the song, actually. It's not connected yet.
Oh. I don't think it's on. Yeah.
Click one more time.
Oh.
It's only 25 minute marker. So now, over time, we can...
Over the course of the day, each frame is an hour.
Yeah, so over one day, we're starting to see whether latency is increasing or decreasing, or whether
big circles are high latency.
Yeah, and whether things move on the animation here. Now we quite naively took 8 months of data and ran it through a Python script, and then we killed that and went back to a day. So there's work to be done about optimization, but the bottom line out of this, sort of final deliverable here is that things do change over time, and if we can build this up to actually show nodes being added to the network, physical nodes that is, and or failures in the network, we should be able to visualize in some way that happening in using this method. And then we're done, because that is... How do you get back to the last slide? We're done. Okay. That was the last slide.
And I also made some hardcore music from it.
Yeah,
but we can listen to it later.
Okay.
Yes. Oh, and there, I apologize. We actually did have one other piece, but no time. Bring it up on your laptop. Sorry.
That's no problem.
Thank you. Well, yeah, cool videos with moving dots.
How applicable would this be to non-Anycast destinations?
We're an Anycast group. So
okay, so let's assume an Anycast cloud of 1. Would it work?
I think the measurements are the same sort of thing.
The measurements would be identical. I think it would just show you that people are far away from that single point, which is valid.
Well, if you compared the speed of light line, you could look to see people that are poorly served, perhaps. Well, at that point, you're really not looking at absolute differences. You're looking at spreads.
Or
so the graph would show you that.
Or it would point out the misgeolocation of the probe if you're sure about the destination.
I think
it can be.
There's that's a good point. Anything below the line is faster than the speed of light, and therefore the probe is just
we did find
lying.
one of those. So
I think
we did find one.
They exist.
Another thing that seemed to be new that, like, to Martin at least, was Martin had previously been looking at this stuff on maps of the Earth, and we started doing it with things that don't really show geography in the same way, and it's another way of looking at it.
It turns out if you remove geography, which I had never done, it turns out to be quite valuable because you sort of lose that distraction. You actually look at it more interesting.
So in a theoretical use case, if you are, say, a content delivery network and you have a big authoritative DNS infrastructure that is announced via Anycast IPs, if you're trying to decide where to deploy next, and you're looking at the one chart with sort of the diagonal line, are you looking for things that fall up that line or above it? What are you choosing? What's your guide if you're that deployment guy and you're saying, okay, which data center should I go to next?
Right. So it turns out, just as a background to that, we work for competitive companies, to a certain extent, in a tiny, tiny vertical. You deploy using your own environment, and you also outsource part of your Anycast. So there's actually really a commercial component to us. There's no doubt about that. The reality, which is why we all ended up together, the reality is that we think in this graph here, given some more processing in visualizing it, you will see a cluster of data that says you need an Anycast node in this to service these guys. And what we did was I think we proved that the Canadians don't have a server in Montreal, or at least we inferred that, and sort of said that would be useful. But there was definitely data on one of the graphs that said...
So are you looking at the city names up and to the right as places you want to choose to
what happened is we
deploy
saw this on a
bring them
different
down?
graph with different data, and there was... Do you remember what it looked like? There was a cluster that was like over here.
Yeah, way away from the line.
And that means that it has really bad response time, and that's partly because it's a bad bad network, probably, and partly because it's far away from the best server.
Yeah, we saw a lot of Canadian probes ending up in London, for example, London, England, and that was an obvious cluster to look at. So.
Yeah, and so there was definitely something that you could visually see out of this.
And the opposite is quite interesting. We saw a bunch that were going to very far away systems, but the response time, not this one, but the other one, the size of the bubble was the response time. The response time was still quite low.
Yeah.
And so we can understand why it was going to such a bizarre location.
Yeah.
We're out of time.
Yeah.
Thank you.
Thank you. Thank you.
Okay, cool, thank you. Yeah, we could do that. Some fresh air. All right. All right. Good. I mean, nothing can travel faster than light. Well, maybe I've seen Star Wars, but anyway. So next one is Katja and Michael, and they're gonna tell us a little bit about a RIPE map, in a way, right? Is that correct? Okay.
Okay, it works. Okay. So it's a pretty low resolution.
Zoom out.
Yeah. Really, it's bigger than. What kind of resolution is that?
I think it's 800.
800. Okay.
Oh, I think I was
Apple
joking
minus
when
is your
I'm
friend.
Well, it doesn't work for maps, I think.
Okay. That's good. So actually, we worked on with Atlas before, and one of the tools that I used the most time was the probe map. And well, the probe map has a lot of disadvantages. Specifically, it's pretty slow. It uses Google Maps, and also the clustering makes it really uncomfortable to actually find stuff in there. Always the moving parts. So there are ways of actually drawing thousands of points on a map, but you have to do it totally differently, not with that one. So we used leaflet and generated a canvas layer. So it's generating map tiles on the fly, and the code is already on. The code is already on GitHub, if you like, and this is the current version of the map. I'm not sure. It's not that good resolution if you look at that. Definitely looks better. So actually, these are all the nodes on all the probes from right now, and you can zoom in without any latency. You can click on the node, get the same information like the old map, but it's much faster. You can also, a typical problem of maps is if you have something like 20 probes at the exact same location, you just see one dot or one pin. So I added a small algorithm that's automatically distributing dots in. Okay. It's actually a fractal algorithm, but whatnot. So no, I think. You can add other fractals, but maybe one person. But this time, okay, no, it's just simple blocks. So now every dot is actually clickable, and also there's some animations on that because we want to show that you can actually use the map for different type of stuff.
Yeah, I want to work with the streaming API for, I think I have many ideas about this in my mind, like which probes are stable and unstable, and what we do was using the streaming API and showing the current events that are coming in or out. And also I've added a pie chart on the right, where you see all the countries, and now you're not seeing which country it is because of the beamer is not the best.
You can kind of see it.
Yeah, actually here are also the country types into this, that you have like an overview how many probes in a country are online or offline. And I unfortunately have not the time to connect the events from the map servers to the SVGs of the pie charts. I want to something like a visual linking, that you are having an idea where was the event on the map and how it does it affect to the bar chart, the pie charts. Yeah, it's ordered right now, the pie chart, with how many props are online in a country. So the props with the most online countries are on the top, and yeah, actually,
yeah,
I forgot something. No,
that's basically this.
this is basically what we are seeing. Yeah, and I want originally show the stability, but with the stability of a probe, you have to, logging the data and you have to know what it means instable, like many disconnects over a short time period. But yeah. It was.
But the basic idea is that it's a generic tool that you can use for everything. For example, if you're pinging a specific IP address for multiple probes and using colors to show the ping times and stuff like that. So it should not be a single-purpose visual tool, so more like a general module you can use for whatever you want. Yeah, that's basically it.
Thank you.
And is this showing data in real time? I noticed some animations with sort of like a poof coming. Is that something coming online?
Yeah, this is streaming API behind.
Streaming
so
right now. Okay.
Everything that comes through the streaming API is showing on the map.
Okay.
So it's always up to date.
Yeah, the dots behind is the dump of all the props from a current state. And then if something is happening, the color changes. I think we have not the evident and never active.
No, we disabled them.
Yeah, we disabled this.
And back in your code, what were the selection variables that you used?
What kind of selection?
So is there anything you're just doing latitude, longitude? Are you able to constrain the data to, say, just look at Africa?
Yeah, of course, yeah. Well, it's a hackathon, so we will have to hackathon this code. And currently, I'm getting the probes, and now here's some simple filter in there, for example, status code, and then here's a set color function. Yeah, but you can use anything else.
Okay. Cool.
There's not yet a simple API, a simple way of coding it, because you really have to hack it. But if you clean up the code, it's much more easier to work with that.
And one other question for the pie charts that were on the right-hand side. You said they were ordered, so the top left would be the highest number.
Yeah, let's show. We have also a little tooltip of it. So if you hover over it, you see which country it is, how many are online, offline, and how many props are in total. I just count the props that are online, offline. So
not abandoned.
Yeah, right.
And not connected yet.
And not connected yet.
Okay.
This also, yeah.
I would prefer to see it in alphabetical order so that I can actually find the country rather than.
Oh, you would have to make a guess about how many probes are online, and then you can.
So is that easy to reorder in any way?
Of course, this would be the best thing that you can give to the user to choose if I want an alphabetical order or do I want a order how many props are currently online or offline, and would be also nice if I'm not adding how many props on total and how it's affect to how many props are online. So if you're adding this like a score, you can also order it and maybe you get a nice pattern out of it.
I would also like to have the instead of fractals, the game of life pattern.
Yeah.
So props are spreading somewhere on there with the glider to do. That's idea.
Is it really a good idea to provide that much granular detail about where the probes are geographically located and whether they're online or offline? What do you think are the possible privacy implications this could have to the people running the probes?
I think it's not then the actual longitude and latitude, so maybe there's a little bit I'm sorry?
It's a bit vague, I think.
Yeah. But I want to show it on something like a map, because if there's something happening right now, you see it on the fly, like because you have the streaming API behind, and this was why we choose this longitude and latitude stuff.
You could reduce the resolution of the latitude, but there's something happening. Oh no! It's a nuclear war. No.
I'm assuming that it is relatively easy to tie this into results instead of being online and offline. So we have a whole lot of maps that show, I don't know, a dozen different colors depending on what the result is supplied by the probe. So it's very interesting. The other question is, can you reapply clustering if the user would want it?
I could do that, yeah, but I'm not sure if... For example, the clustering here, usually the clustering here, it works based on, there's this map of dots, and then it tries to find clusters in there. And
It's pretty dumb in that. But.
Yeah, so it would be much better, for example, cluster it by every probe in Poland. Yeah, so for example, by country. So you can do a much smarter clustering.
So based on that, clustering by country is easy, difficult?
Yeah, we can do it. Give us half a day or something like that.
Deal.
We're actually
And
out of
money.
time.
Oh, what no
And food.
Yeah, good stuff.
Okay, cool. Yeah, might the strongest probe survive? So after we saw 5 presentations, I think we deserve kind of a break and also give the jury some time to digest the information.
Is there one proof lesson?
No, we just make a short break. So I would suggest that we're gonna make a 5-minute break and we're gonna see us back in the room in 10 minutes, okay?
Who's next?
It is the disco team. Well, I mean, the break is 5 minutes, but I guess until we are all back, it will be 10 minutes.
Actually,